Hey guys, here we have a very commonly used function that we want to implement. Given a number a, we want to store the bits of a in reversed order in b. So the leftmost bit in a would become the rightmost bit in b, and the rightmost bit in a would become the leftmost bit in b. Alright? Just a brief background, this function is usually available to us developers in the form of an intrinsic function, which basically means that the hardware provides us with an API that does this task very efficiently for that particular hardware. But since we also have to use this function quite a lot in simulation environment as well, we occasionally end up implementing this function. Okay, first we'll look into a solution for this problem and then have some optimization discussions. If you want to try this question yourself, please pause this video now and start coding. Alright, in this question, the number a is unsigned 32-bit type, but we will take a simpler example of 8-bit number a, which we will have as a equal to 0, 1, 1, 0, 1, 1, 0, 1. The output in this will have to be b equal to 1, 0, 1, 1, 0, 1, 1, 0. Okay, so the total bits in the number is 8. Let's index them as 0, 1, 2, 3, 7. Okay, now let's visualize what we want to do. First, we want bit in index 0 and then place it in the leftmost bit of b, that is in index 7. First step is extraction of this bit 1 from a. So we need a mask which will take out only one bit from a, that is the rightmost bit from a. Therefore, the required mask will be 0x1. 0x1 in binary is 00000001. If we do an AND operation between a and the mask 0x1, the result will be the rightmost bit of a, isn't it? So we do a and 0x1, and the result in this example is 1. Now we want to store this bit in b. Let's initialize b to 0 first. b equal to 0. Now we want to shift to the left this number 1 by 7, such that this 1 is stored in index 7 in b. So we have to do 1 left shift by 7 and store it in b. This will result in b equal to 1, 0, 0, 0, 0, 0, 0, 0. Now we want to extract the index 1 bit from a. The index 1 bit here is 0. For this, we need to do shifting and masking. First, we will shift a to the right by 1 bit. So the index 1 bit will come to the position of the rightmost bit. And then we will use the mask 0x1 to extract this single bit 0. So we do a right shift by 1 and it with 0x1. This will result in 0. Now to store and place this in index 6 of b, we need to shift this 0 to the left by 6 positions. Also, b already has the first bit 1 stored in it already, and we do not want to disturb that. Therefore, we will use an OR operation. We will do b equal to b or 0 left shifted by 6. This will result in b to be equal to 1, 0, 0, 0, 0, 0, 0, 0. The second bit 0 here is actually the index 1 bit of a. Great, now I think you got the logic, so we will quickly go to the last step required. For extracting the index 7 bit from a, we will first shift a by 7 positions to the right, such that the leftmost bit comes to index 0, and then we will use the mask 0x1 to extract the single bit 0. So we do a right shift by 7 ANDed with 0x1. This will result in 0. And to store and place this in index 0 of b, we need to shift this number 0 by 0 positions. That is, we do not need to shift it. We will do b equal to b or 0 left shift by 0. Alright, here in the first step we can write this as a right shift by 0. So you can see a symmetry between extraction from a operations and placement in b operations. We see here we have right shifts by 0, 1, 2, 3, 7, and here we see the left shifts by 7, 6, 3, 2, 1, 0. So for each step of extraction and placement, if we say this here, this is index I, then on the other side, this is always 7 minus I, right? When I is 0 here, we see we need 7 here. Great, now we can write down the 3 lines of code for this problem. First, of course, is b equal to 0. And then we need a loop that will go through the bits in A one by one. So for I equal to 0, I less than equal to 7, I plus plus. We need b equal to b ORed with the extracted bit, which is A right shifted by I ANDed with 0x1. And this we need to place in B, for which we do left shift by 7 minus I. This will solve the problem if the size of A is 8 bits. Now for our question, A is a 32-bit number. To make your function more generalized, we could use the inbuilt C++ size of operator. We could replace this number 7 here and here with size of data type into 8 minus 1. If data type is a 4-byte integer, then size of operator returns us 4. And 4 into 8 minus 1 is 31. Therefore, you can replace the 7s here with size of int into 8 minus 1. Now let's talk a bit about optimization. This function actually has various optimized forms. We will quickly explore one idea. Alright, if the input A is 32 bits, but if you know that the value in A most of the times will be very small and would require only 7 or 8 bits. In such conditions, what we could try to do is we do not loop through all the 32 bits in A. Instead, we will have a variable t equal to A, and then on each iteration of this loop, we will right shift t and then check if t becomes 0. So t equal to A, t right shift by 1. If t equal to 0, then break. This way, the loop will iterate only 7 or 8 times. There are various other optimized methods to solve this problem, and you could figure out one which would suit your requirement. Do let us know how you choose to solve this problem in the comment section below. Alright, that's it. In the next episodes, we will visit some more interesting bit manipulation problems. If you found this video helpful, do subscribe to this channel and hit the like button. See you!